Good morning, respected teachers. Today, I, Bhagyashree Kalita, and Ilyas Hussain are going to give a final year project presentation on investigation on direct torque control strategies of three-phase induction motor and permanent magnet synchronous motor. So these are the contents. So first, let's move to the introduction part. So nowadays in industry, electrical motor drives are widely used as variable speed drives. Among several types of electrical motors, three-phase induction motors and permanent magnet synchronous motors occupy a prominent place because of their low cost, reliability, high efficiency, robustness, low maintenance, etc. Induction motor proved its importance since its invention and has been used industrially and commercially because of its advantages. Permanent magnet synchronous motors are also becoming attractive because permanent magnet synchronous motors are used in places that require fast torque and torque response and high performance operation of the machine. The behavior of the machines are often very complex and it's very difficult to measure its state variables like flux. So to reach the best efficiency of the motor drive, some advanced control algorithms are required to control the flux and torque of the machine. So in our project, we have used direct torque control strategy to control the flux and torque of the machine. Objective. So our first objective is to understand and modeling the sinusoidal pulse width modulation inverter circuit. After that, modeling the direct torque control scheme of induction motor and permanent magnet synchronous motor. After that, torque, flux and speed estimation by sensing machine terminal voltages and currents of both induction motor and PMSM. To improve the performance of an induction motor and PMSM with precise speed tracking and smooth torque response by implementing DTC scheme. Overview of VFD control platform. This figure 1 shows overview of VFD control platform. So VFD control platform or variable frequency drive is nothing but a type of adjustable speed drive which is used in electromechanical drive system to control AC motor speed and torque by varying motor input frequency and voltage. So this platform is divided into two types. One is scalar control and another is vector control. Scalar control is V by F control. In V by F control, voltage and frequency are changed at the same time. That means we have to keep the V by F ratio constant. And this on the other hand, vector control strategy is divided into two types. One is FOC, that means field oriented control, and another is DTC, that is direct torque control. This direct torque control is again divided into three types. One is DSC, that is direct self control, SVM, space vector modulation, and SPWM, which is sinusoidal pulse width modulation. In FOC, what happens? FOC controls the speed or torque of an AC motor by controlling the stator current space vectors. But when we come to DTC, it doesn't control the flux through controlling the current. It directly controls the flux itself. So DTC is sensorless. No speed or position encoders are required. It only requires voltage and current measurements. So this reduces cost and improves reliability. And DTC does not require a modulator also. So processing time is reduced here, which improves torque response. So because of these advantages, this control strategy DTC is used widely to control the speed and torque of motor drives. Principle of DTC. So what is the principle of DTC scheme? The basic principle of DTC is to directly select stator voltage vectors according to the torque and flux errors. These torque and flux errors are the differences between the references of torque and stator flux and their estimated values. Actually, what happens in a voltage source inverter fed DTC AC drive, the torque and flux parameters can be directly controlled by the application of the proper stator voltage space vectors from the inverter. The governing equation for torque for this scheme is due to the interaction of stator and rotor fields. Torque and stator flux linkage are computed from measured motor terminal quantities, that is stator voltage and current. An optimal voltage vector for the switching of VSI is selected from the 6 non-zero voltage vectors and 2 zero voltage vectors by the hysteresis control of stator flux and torque. So now let's move to the block diagram of DTC. Actually, the DTC scheme is comprises of different blocks. The measure are the flux calculators, torque calculators, hysteresis comparators for flux and torque, and the switching table, etc. So at first, the phase voltage and phase currents are fed to the motor model, which uses advanced mathematical algorithms to produce exact values of the stator flux and motor torque. After that, the actual torque and flux values are fed to the torque and flux comparators. In torque and flux comparators, the actual torque and flux values are compared with the reference values of torque and flux. The output obtained from these comparators, that is torque and flux data signals, are fed to the optimum voltage selector. The optimum voltage selector chooses the optimum voltage vector from a lookup table, and based on this sends pulses to the inverter, semiconductor, switching devices to maintain or change the motor torque as required. Hysteresis controller. So the main role of hysteresis comparators are to determine whether an increase or decrease of flux or torque is required or not, depending on whether the torque or flux errors are outside the hysteresis band or not. Hysteresis is important for producing stable switching behavior in a comparator circuit. This hysteresis is aided by including a positive feedback loop between the output and input. Yeah, the figure 3 shows a hysteresis comparator. Here, if the input voltage reaches the threshold, that is VOS, from the negative direction, the controller switches from 0 to 1. When the input reaches VOS plus VH by 2, here VH is the hysteresis voltage, then the new switching threshold is changed and become VOS minus VH by 2. The comparator output remains stay at 1 till the threshold VOS minus VH by 2 is reached, coming from the positive direction. Noises concentrated around VOS cannot allow the controller to change its state unless it exceeds the limits VOS plus minus VH by 2. This hysteresis controller is of two types. One is flux comparator and another is torque comparator. So first we will discuss about the flux comparator. A two-level hysteresis comparator is used for flux regulation. The bandwidth of the flux comparator is 2h psi s, which is shown in figure 4. That is, band limit is from minus h psi s to plus h psi s. The flux error is the result of difference between reference flux and estimated flux. The flux error del psi s is equal to psi reference minus psi estimated. If this error exceeds the hysteresis band limit, then the output of the flux controller is high, that is 1. If the error lies within the limits, that means if it is between minus h psi s and plus h psi s, then the output is low, that means 0. High output means a flux increase is required, while low output means flux decrease is required. Next, we will move to the torque controller. So, torque controller is a three-level hysteresis controller. The bandwidth of the torque controller is 2 del TE as shown in figure 5. Here the range is, the bandwidth is from, limit is from minus del TE to plus del TE. The torque error is the result of difference between the reference torque and estimated torque. The torque status has three values, 0, 1 and minus 1. When the torque error is less than minus del TE, then torque status will be minus 1. That means torque decrease is required. When the torque error is greater than plus del TE, that means torque status will be 1. Then torque increase is required. When torque error is within the hysteresis band, that means between minus del TE and plus del TE, then torque status is 0. That means torque should be remain unchanged. So this is all about hysteresis comparator. So now voltage source inverter. So actually this voltage source inverter is an important part of any DTC drive. The inverter converts the DC to AC through power electronic devices such as IGBT, MOSFET, etc. The VSI used in this study consists of 3 legs, 2 switches at each leg. In DTC, switching action takes place as per the switching pattern of switching table. So here the switches are gated at regular interval of 60 degree. The 6 switches are divided into 2 groups. Upper 3 switches as positive group, S1, S3 and S5, and lower 3 as negative group, S4, S6 and S2. In VSI, only one switch of each leg will be turned on. When the switching signal S equal to 1, Then the upper switch turns on, and when S equal to 0, then the lower switch get turned on. There are total 6 switches giving 8 total states for the output. These are referred to as the base vectors. So the next slides will be explained by Ilyas Hussain.
Thank you, Vagyasi. So here the connection of inverter circuit with the three-phase induction, three-phase stator winding is shown. So here we have taken three switching status SA, SB, and SC. If the upper switch, for example, if SA is on, then we will take SA is equal to 1. If this lower switch is on, then we will take SA is equal to 0. And this will be same for the other switch also. So here we have also shown how voltage vector switch, we have taken an example of switching status showing the voltage vector. So in figure 8, we have taken example of switching status 100. That means phase A is connected to the positive side of the battery, phase B is connected to the negative side of the battery, and phase C is connected to the negative side of the battery. So here the DC voltage distribution is shown. The voltage between phase A and neutral is 2 by 3 BD, and similarly for BBN is equal to minus 1 by 3 BD, and BCN is equal to minus 1 by 3 BD. So taking phase A as reference, we have got the value of B1, that is switching status 100. The B1 is magnitude is B1 is equal to BD, and it is along the direction of phase A. Next slide. So here we have shown the all possible switching status, that is for 000, for 100. So here B0 and B7 are called as zero voltage vector, and from B1 to B6 are called as non-zero voltage vector. So as I explained in previous slide, how 100 for 100 is B1, and the voltage distribution between BAN is equal to 2 by 3 BDC, BBN is equal to minus 1 by 3 BTC, and so on. So here all the um, um, possible switching status and respective voltage vector is shown, and also line to neutral voltage and line to line voltage are also shown here. Next slide. So here in this diagram we can see that the B1 100 is along horizontal direction, along direction of alpha, and B2 B3 B4 B5 B6 are shown here. So sector detection is one of the very important part of DTC. To select the suitable voltage vector, we need to look at the flux vector. So the alpha beta plane, that is voltage vector plane, is divided into 6 sectors. Each one is expanded by 60 degree. So by the help of flux linkage vector in alpha beta plane, the location of stator flux is possible. The sector angle can be calculated as tan inverse of psi s beta divided by psi s alpha. Psi s beta is flux linkage component along beta direction, and phi s alpha is flux linkage component along alpha direction. So here the starting angle for sector 1 is minus 30 degree to plus 30 degree, and the for all the 6 sector is given in the table 2, and it is also shown in the alpha beta plane in figure 9. Next slide. So here we have selection of the stator voltage space vector. So here we have taken an example, and with the help of this we will try to understand how can we select a voltage vector. So here we have taken example of sector 1. Flux linkage is present in sector 1. For this, for increasing the torque and for increasing the flux, we have to select voltage vector B3, and for similarly for increasing the torque and for decreasing the flux, we have to select voltage vector B2. And the and others also given in the table C. Next slide. So switching table. So switching table is also called as lookup table. Actually, it is the main part for selecting the voltage vector. So the voltage vector table receives input from the 2-level and 3-level hysteresis comparator and generate appropriate switching state vector in the inverter from the switching table. The main function of this is to keep the stator flux in the respective hysteresis band. For psi is equal to 1, that is flux status 1, and it is the output of the flux controller, and torque status 1, it is the output of the torque controller. So that means flux status 1 means we have to increase the flux, and torque status 1 means we have to increase the flux. So as I explained in the previous slide, that for sector 1 we have to select B2, and similarly for other sector also, let's say sector 2 B3, sector 3 B4, and for all the possible status like for flux status 1 and torque status 0, that means we have to increase the flux and torque remain unchanged. For this we have to select 0 voltage vector, that is B0, and similarly all of these are given in this table. Next slide. So simulated models. So here we have simulated Sine PWM circuit with induction motor. We have simulated DTC of 3-phase induction motor. Also we have simulated SPWM with PMSM and DTC of PMSM. Next slide. So SPWM inverter circuit. So in this figure, we have shown the simulated diagram of comparison of carrier signal and reference signal. Here the carrier signal is triangular wave whose frequency is 5 kilohertz, and the reference signal is sine wave. So here the sine wave, the phase of sine wave is 120 degree is apart from each other. So here we have compared the triangular wave and sine wave, and we got the value of we got the 6 switches, switch 1 to switch 6, which will be used in the inverter circuit. Next slide. So here the comparison of carrier signal and reference signal is shown. The carrier signal, that is triangular signal, and the reference signal, that is sinusoidal signal, are compared, and when the this carrier signal will be more than reference signal, then we will get PWM output with high value and low value when it is less. So here the green line shows the PWM, green waveform shows the PWM output of this simulated carrier and reference signal. Next slide. So among the 6 switches, we have shown here only 2 switches, switch 1 and switch 4. And the waveform switch 1 and switch 4 is shown in figure 13. Here when switch 1 is high, then switch 4 will be low, and vice versa also. Next slide. So here the parameter parameter of induction motor that we have used in the simulation purpose. The power is 5032 output, the pole pairs is 2, and the rest of this parameters is given in this table 5. Next slide. So here we have shown the simulated diagram of SPWM induction motor. SPWM with paired with induction motor. Here we have converted DC voltage into AC voltage for feeding the induction motor. The gate pulse are used the 6 switches. The PWM output from the The PWM output is used as gate pulses for the IGBT switches, and this is how we converted DC to AC voltage, and it is fed to the induction motor. Next slide. So here the simulation result of this simulated diagram. The simulation here the waveform of stator current, waveform of torque, and waveform of rotor speed is shown in this figure. So here initially before 0.4 second there is a ripple in the current, and after 0.4 second, so it is quite stable. So for the torque, um, before 0.2 second there is a ripple, and after 0.4 second, the torque is nearly equal to 0, as we have applied um, we have used no torque. It is in no load condition. And the rotor speed, so rotor speed before 0.4 second, the rotor speed gradually increases from 0 to 157 radian per second, and after 0.4 second it is constant and nearly equal to 157 radian per second. Next slide. So next will be explained by Bhagyasri Kalita.
These voltages and phase currents are transformed into two stationary reference frames of voltage and current, that is V alpha, V beta, and I alpha and I beta. So here, after that, the psi and m, that is flux and torque, are calculated by using some machine modeling equations of flux and torques. After that, psi alpha and psi beta are also calculated by using equations. Then this psi alpha and psi beta are fed to the sector detector subsystem, where the required sector is detected, and the output of this sector detector is fed to the voltage vector selector. On the other hand, the psi, that is flux, and m, that is torque, are fed to the flux and torque controller, where they are compared with their reference values of flux and torque. The output of these flux and torque controllers are given to the voltage vector selection subsystem, where an optimum voltage is selected on the basis of the switching or lookup table. After selection of the voltage vector, it sends pulses to the inverter switches, and the inverter is then fed to the three-phase induction motor. So these are the machine modeling equations that we have used for the simulation of DTC scheme. So this figure 17 shows a simulated model of phase voltage calculation. So here for this simulation, we have used three equations of VA, VB, and VC. Here the equation of VA, VB, and VC are VA equal to VDC by 2 into 2 SA minus SB minus SC, VB equal to VDC by 2, 2 SB minus SA minus SC, and VC equal to VDC by 2 into 2 SC minus SA minus SB. So by using these three equations, we have simulated this phase voltage calculation. Uh, if we consider the first switch, so when first switch is on, then we have to consider VDC by 2, that means 600 by 2. We have taken the DC voltage source as 600 volt. So after that, if switch 1 turns off, we have then it will be 0. So in this way, the other VA, VB, other phase voltages VA, VB, and VC are calculated. After that, figure 18 shows voltage calculation in alpha beta axis, and figure 19 shows current calculation in alpha beta axis. These two simulated diagrams are also designed by using the equations of V alpha, V beta, and I alpha and I beta. The equation of V alpha is VA minus half VB minus half VC, and equation of V beta is root 3 by 2 VB minus VC. So similarly, this current calculation in alpha beta axis is also done by using equations of I alpha and I beta, which are I alpha is equal to Ia minus half IB minus half IC, and I beta is equal to root 3 by 2 IB minus IC. So as a result, we have found this waveform of V alpha and V beta. So here the first waveform is of V alpha and second is of V beta. So in the first waveform, the maximum voltage is 600 volt and minimum is minus 600 volt. And in V beta, we have found the maximum voltage is 500 volt and minimum as minus 500 volt. And again, we have also found the result of I alpha and I beta, which is a pure sinusoidal waveform. So here, in the first waveform, there are some high current up to about 0.62 second. Then after then the current decreases and this current is maintained. After that, figure 22. This figure 22 shows simulated model of flux and torque calculation. This model is done by using equations of psi alpha, psi beta, and flux and torque equations. So equation of psi alpha is integration of Vs alpha minus Rs Is alpha into dt. So Vs alpha is the stator voltage in alpha axis, and Rs is stator resistance, and Is alpha is stator current in alpha axis. And psi beta is integration of Vs beta minus Rs into Is beta dt. So here Vs beta and Is beta are stator voltage and stator current in beta axis. So the equation of flux is equal to root over psi alpha square plus psi beta square, and the equation of torque is T equal to P into psi s alpha into Is beta minus psi s beta into Is alpha. Here P is the number of pole pairs. So by using these all equations, we have simulated this diagram. And after as a result, we have the waveform of psi alpha and psi beta comes out like this. So here the maximum value of psi alpha is 0.9 and minimum is minus 0.9 in both the waveform of psi alpha and psi beta. Sector detection. So this figure 24 shows a function of sector detection. The whole sector detection part is implemented as a program in MATLAB function. So here this is the program. So here n is the number of sector and theta is the tan inverse of psi beta divided by psi alpha. So how will I select this? So first, if theta is greater than or equal to minus pi by 6 and theta is less than pi by 6, that means if theta is in between minus 30 degree to plus 30 degree, then we will select sector 1. That means n equal to 1. If again theta is greater than or equal to pi by 6, that means if and theta is less than pi by 2, that means if theta is in between plus 30 degree to 90 degree, then we will select sector 2. That means n equal to 2. So in this way we have to select the other 4 sectors up to sector 6. So as a result, the waveform of these sectors comes out like this. So this is the waveform of sector detection. So this figure 26 shows simulated diagram of flux controller and figure 27 shows simulated diagram of torque controller. Thus, the flux controller is a two-level hysteresis controller. So we have used one relay for the simulation of flux controller, and torque controller is a three-level hysteresis controller, and we have used two relays for the simulation of torque controller. And the waveform of this flux controller and torque controller are shown in figure 28. So here, if we consider the torque controller waveform, it rises from 0 to 1. 1 means we have to increase the torque, and 0 means we have to that no torque should be remain unchanged. So in this way, a torque controller and flux controller operates. Simulated model of switching table of DTC. So this is the um, so here that there is a MATLAB function where the whole lookup table or switching table is implemented as a program. So this MATLAB function is then connected to the multiport switch where the 6 non-zero voltage vectors and 2 zero voltage vectors V0 and V7 are connected. An optimum voltage vector is selected by using the MATLAB function of lookup table. Suppose the voltage vector V1 is selected. So the 6 switches will send pulse to the inverter switches against the voltage vector V1. So that means for each voltage vectors, for V0 to V7, there will be six switches against each voltage vector. Suppose we have considered a voltage. Suppose we will select voltage vector V1. Then the coordination of V1 is 100. That means switch 1 should be turned on, switch 3 and 5 should be turned off. So here we can see V1 is 110001. So in the first switch 1, that means switch 1 is turned off. So switch 3, the third place is 0. That means switch 3 is turned off. And in the fifth place it is 0. So switch 5 is turned off. So in this way, we have to select the voltage vectors. So this is the comparison of switch 1 and switch 4 of the DTC. So when switch 1 rises, switch 4, when switch 1 turns on, then switch 4 turned off. Because we know that in a voltage source inverter, in one leg, one switch is turned on and one switch is turned off. So here, this is the comparison of switch 1 and switch 4. So after that, the next legs will be explained by Elias. Hello?
Hello.
Uh,
Here, here the simulation result of DTC of induction motor at no load condition is shown in figure 31. Here the waveform of flux, torque, and rotor is shown. So in uh, while doing the simulation, we have taken the reference flux as 0.9 and torque at no load condition, and rotor speed is 100. So here we got the flux value nearly equal to 0.9, which is uh, which is close to the reference value, and also the torque is 0, and the rotor speed is also nearly equal to the reference value. That means from this waveform we can conclude that we got the we are able to control the torque, rotor speed, and flux of this induction motor. So next slide. So here we have taken another reference value where we have taken the torque value is 10 Newton meter, and rotor speed is 150 radian per second, and flux is 0.9. So here also we got the value of flux, torque, and rotor speed nearly equal to the reference value that we have taken. So in the waveform of torque, we can see that initially there is a high torque, which is greater than 10 Newton meter and equal to 20, nearly equal to 25 Newton meter. It is due to the in an induction motor, um, there is a high current initially. So to prevent this, we use resistance and to decrease the current. For this, the torque value increases initially, and after that, after some time, it becomes nearly equal to the 10 Newton meter. So here we have also able to control the torque, rotor speed, and flux. Next slide. So PMSM, here the different types of PM electric machine has shown in this figure. Next slide. Next slide. The parameters of this PMSM has shown in this table. Here the stator phase resistance is 0.0485 and the pole pair is 2 and so on. Next slide. So here the simulated model of DTC of PMSM as shown in this figure. So we have already done the DTC of induction motor. After that, we have also simulated the DTC of PMSM. The 90% work of this DTC of PMSM has been done, but due to some small error, we are not able to showing the result here. So we are now working on it to figure it out what is the problem, and um, we'll fix it. Next slide. So here the experimental works. So the architecture of DTC has shown in this figure 35. There are basically three major parts in the architecture. One is power circuit part, second is measure and signal conditioning part, third is control circuit part. So here we have tried to design control circuit part of this DTC. So it was intended to do control circuit part. The control circuit is considered the brain of the system that provides necessary commands action to make desired criteria and assure stability. For this control circuit, the DSP is most commonly used in motor control area. DSP allow complex arithmetic operation to be executed. The DSP that we have used here is TMS 320F2379D. It is a 32-bit floating point microcontroller unit designed for advanced closed loop control applications such as industrial drives, servo motor control application, digital power application, converters, and power communication. Um, So here the different parts of this DSP board has shown in this figure in the right side. Here the number 3 is a microcontroller which is TMS 320F2879D. Number 2, 8, 9, 6 are the GPIO pin. And all of the other parts are shown in this figure also. So, so we have tried to understand the DSP board, and we have practiced some program on it, and to control the parts of the DSP board. For this, we have first tried. Next slide. We have first tried sine wave generation, generating the sine wave. For this, we have used Code Composer Studio to compile on it. So the program of the sine wave generation is shown in this figure 37. Next slide. Next slide. Here the waveform of this sine wave is shown in this figure. The amplitude of this waveform is 1000, and then this waveform we got by executing the program that is shown in the previous slide, and it is done by CCS. Next slide. So there are 3 LEDs in this DSP board. Among the 3 LED, two are controllable. These 2 LED are D9 and D10. D9 LED is connected to the GPIO pin 31, and D10 LED is connected to the GPIO pin 34. So here here we have blinked the LED of D9 and D10 by using both Code Composer Studio and MATLAB platform. So here next page, next slide. So here the LED blinking photograph has shown in this figure. So here the LEDs blinked. Next slide. So here till date we have simulated the SPWM inverter circuit with the induction motor and DTC of induction motor We have also simulated the PMSM, but due to some error, it is we are not able to show the result. Um, we'll try to complete the whole DTC and DTC of PMSM also, and as an extension of this work, we'll implement the DTC drive system by using and we'll implement the DTC drive system, and we'll design the control circuit part of this DSP, and we'll try to complete it in coming future. Next slide. So these are the references. Next slide. Thank you.
To perform a DTC through your DSP board, then what are the
Yes, sir.
parameters you have to sense through for the calculations?
Sir, first for this calculation, we have to measure voltage and current, sir. For
Voltage
this,
and current
we have,
only?
yes, sir. For voltage, voltage, the calculation of torque and other
Then
speed.
how it will be happen? Like if you will calculate, say you will implement a voltage sensor and a current sensor, okay, right? After then you
Yes, sir.
will feed these two values to the DSP processor, है ना?
Yes, sir. Yes, sir.
After then what are the process will happen? How you will connect it? Those are the analog signals. So how you will convert it to a DSP related parameters?
Yes, sir. First, we have to step down the current that is measure that is taken from the motor. Then
Okay.
the maximum value of this DSP that can taken is minus 5 volt, minus 3.3 volt to plus 3.3 volt. That means we have to
Okay.
use voltage sensor,
Mm-hmm.
and the value should be between minus 3 to plus 3.3.
Okay. First you will step down those things, right?
Yes,
After
sir.
then,
Yes, sir.
after then,
Sir,
next step,
we
what
have
will be your next step?
Sir, we have to use voltage sensor for this.
No, no, no. That's right. Voltage sensor. Then you will have to step down those voltages. After then, what will happen?
Sir, after then, sir, we have to do program on this DSP for calculating this various parameter.
No,
And
there's the calculation part. There's the in between calculation and in between the parameter sensing. है ना?
yes,
In
sir.
between, is there any analog to digital converters like things will be required? Or no? ADC kind of thing?
Sir, there is already ADC in this DSP board. For independent
No,
DSCs,
no,
there,
that
sir.
is already there. So you will connect it to the those analog signals to be connected to the digital pins.
Yes, sir.
Sorry, ADC pins, not digital pins. है
Yes,
ना?
sir. Analog pin will be connected to the ADC pin to convert it.
Yes, from that you will get the digital values and those will be calculated so that, right?
Yes, sir. Yes, sir.
After then, what the DSP finally DSP what will be the output of the DSP?
So DSP will give the gate pulse. That means um, the
Yes.
control circuit after this voltage vector calculation, which voltage is needed? That is B1 to B6, B1 B6, B1 to B6, and B0 B7. Which one is needed? Which pulse is needed for this optimum torque? That will be given by this DSP board.
Okay. So go to the 45 page. Go to next slide. Next slide. Just next. Is the sine wave. Yes.
45.
So if you want to, so what is your frequency here? Elias?
So frequencies. So yeah, if taken frequency is 6.
Next slide, the waveform. Go to that waveform. Yes, from here you have what would be the frequency? Can you tell that? Below
So
the
yeah,
time axis, na?
so time period will be it is 6.2. Then
Tell me one thing. That is plus 10, 20, 30. These are the in second or millisecond. What? 10 millisecond or 10 second?
Yes,
Okay.
sir. So
Okay.
this value is in milliseconds, sir.
Millisecond.
Yes,
So
sir.
let's say you want to change the frequency, then go to that program part before 45 page. If you want to, let's say you want to change the frequency of that signal, then how you will change it?
Sir, we have to change the time for t is equal to 0, t less than 6.2. Then we have to change it. It will be
No, no. Baba said that is the maximum time, Baba. That is the maximum time. Sin t in place of t value, you want to change the value, na? Okay.
yes, sir.
So you didn't experiment that particular thing, na? How to change the frequency? If you want
Sir,
to change
actually,
the amplitude or frequency, huh? Hmm.
yes, sir, I tried, sir. I gave some sir other waveform.
What
Uh,
triangular?
yes, sir, like triangular something. Sometimes it is some other kind of waveform. So I have tried
Acha.
to understand it, but
In
it's
that
not.
math library file, you will get this is SIG means what? SIG in between inside you written 620. What is the meaning of that 620?
So that means it will go to 620, sir. That means
Up to 620 it will calculate or what?
yes, sir.
So you didn't go thoroughly into it, na?
Yes,
There
sir.
are lots to do. From a simple like programming, yeah, you can do lots of things, right? So you experiment with those things. Those are the actual required things for your work, right? How to change the
Yes,
frequency, how you will change the amplitude of that sine wave, how many signals you can generate from using that math.h.
yes, sir. Sir, I am able to change the amplitude of this waveform by changing the in the last written years six
Now,
I
how much amplitude is there? Go to the
thousand
next slide.
thousand,
Thousand.
sir.
Thousand. Thousand what?
Yes,
Thousand. So you plotted it where? Through CCS, na?
yes, sir. Yes, sir.
Uh-huh.
Yes, sir. In CCS.
Okay. Thousand amplitude can be possible. Okay. If you want to,
Yes, sir.
let's say you plotted it and you saw it in your CCS panel, right? If you want to
Yes, sir.
take this sine wave out from that DS code, how you will do that?
Sir, then we have to do program and um, we have to sir taken through this port, sir. That port in the
Okay,
DSP board.
you have to take it out from the GPI generalized input output pins or other pins will be required like DAC or something like that.
Sir,
These are the digital values, right?
yes, sir. Yes, sir.
Digital values, but multiplied with some constant value, and then these are plotted,
Yes,
as
sir.
I think so. Eh? And then they will, if you want to take it out from a DSP board, like a means you want to see a value from a pin, then it should show like a sine wave at the oscilloscope outside. Eh?
Sir, yes, sir. We have to take through this DAC pin, digital to analog converter pin, sir.
Yes. Okay. Okay, Bhagyasri,
Yes, sir.
go to the switching table. Okay. Tell me, Bhagyasri, tell me something about that row 3.
Sir, row 3.
Yes, sir.
Okay, sir. Sir, here flux status is 1 and torque
Okay.
status is -1. That means
Okay.
flux should be increased and torque should be decreased. So
Okay.
here, if it is decreased, then in sector 1 we will select voltage vector V6.
Okay. Sector
In this
1.
way, in sector 1, then we will select voltage vector V6, and in sector 2 in V1. And
Okay.
in this way, in sector 3 V2, in sector 4 V3, that's way, sir.
Okay. So go to the B6 table, B6 B1 table. I think it is earlier. Huh? The voltage sectors. Yeah.
Sir, this one.
No. Before that, that your the three is sorry 6 different switching. Yes.
Uh,
So can you keep it in B0 and B7 position?
sir, mm, sir means मतलब समझ में नहीं आया.
नहीं मतलब ये है कि can you give the B0 and B7 states to a converter? Means all the switch upper switches will be 0, all the lower switches will be 1, something like that. Can you do
हाँ
it?
सर हाँ सर यहाँ पर SA, SB and SC is 0. That means all switch are connected to the lower switch. So here we
Okay.
have to select voltage vector V0. So here from here we can say that here in figure 8
Mm.
um,
Mm.
all the A, B and C phase will be connected to the negative end. So in
Mm.
this way we have to calculate this and we will find out the VN as 0, VBN as 0
Mm.
by
Okay.
using calculations.
Okay. So you did it in MATLAB, huh?
Yes, sir. Yes.
Yes, sir.
Okay. So okay. Next, anyone else from my side? It's okay.
Okay, Elias.
Yes, ma'am.
All these simulations are done in which software?
Ma'am, simulation is in MATLAB.
Okay, in MATLAB. Okay.
Yes,
Go
ma'am.
to slide number 14.
Okay, ma'am.
Okay. In the sector detection, what does this alpha beta signifies?
Ma'am, alpha beta means these are two stationary frame reference. Actually, we have converted this three phase to two phase. As three phase in three phase, the calculation of this various parameter is very become complicated. That's why we have converted three phase into two phase stationary frame reference. And this alpha beta is um, RAC. That means these are stationary frame reference, and the below are will be in sinusoidal form.
Called Parkes transformation or Clark's transformation?
Sir, Clark's.
Okay.
45 slide number. Yes. So this problem is done in which software? Written in which software?
It is in CCS, Code Composer Studio.
Okay. So this code is for generation of sine wave, na?
Yes, ma'am.
Okay. Here you have written for this double semicolon. So for which purpose this is written?
Ma'am, double semicolon means it is an infinite loop. The for loop will be infinite. That's why double semicolon is used.
Okay. And this t less than 6.2. So what does it mean? For loop this
Yes,
within this
ma'am.
for loop t less than 6.2.
Ma'am, that means the maximum value of t will be matlab, um, this value started from 0 to 6.2, and the increase will be 0.01 in each step.
Okay. So for the sine wave maximum value will be 6.2. Yes.
Yes, ma'am. Ma'am, yes, ma'am.
Show me the graph. So where it is 6.2?
Ma'am, actually, for a one waveform, for one cycle, it goes to 62 below, nearly 62.
What? Go to the program.
For one loop, that is one cycle, this one cycle of this sine wave goes to 62 below, ma'am.
62 value.
Yes, ma'am.
But it is not shown in the web. Okay, go to the program.
Yes, ma'am. Here 6.2 is there. Ma'am, T is multiplied by 10. I and D is equal to T into 10. That's why, ma'am, 6.2 becomes 62 there.
Okay.
No, actually, Elias, it is not so. Actually, this should not. What you have written 620, that should not be 620. For a sine wave, that should be 628. Why 628? Because you see,
2 pi.
SIG, yes, right, 2 pi. SIG is signed bit, and that is will be counting up to 628. 3.14 into 2, that is 628. You will be getting one cycle. And likewise, for your second for loop, it will be 6.28. Okay.
Yes, sir.
Now, if you calculate the next line, that is t equal to t plus 0.01 and go on multiplying with that, you will be seeing that after 628, you will be reaching 6.28.
Yes, sir.
Okay. And the error in this program is shown in your graph also. You go to the graph. You see there is a dip at around 800 in the y-axis. You see at
Yes,
around
sir.
800 there is a dip.
Yes, sir.
There is a sudden dip. That means 8 values are missing from there. It is just resetting before ending 2 pi.
Yes, sir.
Hello,
Yes, sir. Yes, sir.
Ilya,
Sir.
Ilya sir Bhagyasri.
Sir.
You have done a great job and you have presented it very well. But I have a small questions, one, two question. Okay.
Okay, sir.
Okay, sir.
Can you say you are saying that there is uh, hysteresis error in torque and flux in direct torque control? You are saying that na, two hysteresis there, torque
Yes.
and flux.
Yes, sir.
So which flux is this? In three-phase induction motor, there are two flux, na?
Yes, sir. So this is
So
sorry, this is it's a stator flux.
yes, this is stator flux. So Bhagyasri, can you say how the flux will be increase or decrease, and how the torque will increase decrease? How you relate?
How will relate?
कैसे होता है ये? तूने voltage choose कर रहा है कोई switching scheme के लिए ना?
Sir.
You have seven switch seven voltage ना V0 to V7.
Sir.
So how will relate? Torque is increase, flux is increase. How? स्टेटर फ्लक्स इंक्रीज होगा, सपोज स्टेटर फ्लक्स को इंक्रीज करना है, ठीक है
Yes, sir.
ना, टॉर्क को इंक्रीज करना है, कैसे रिलेट करोगे?
सर वो रेफरेंस वैल्यू
Go to the
रेफरेंस
sector
वैल्यू
diagram.
ओके
Go
सर
to the sector diagram. Here. Again, next slide. Next slide. Okay. This you have written the torque increases, flux increases. Different combination are there. Yes or no?
यस सर
तो कैसे होता है ये? जैसे फॉर एग्जांपल मैं V3 सिलेक्ट किया, ओके?
हाँ
यस सर
V3 सिलेक्ट करने से टॉर्क क्या हो रहा है तुम्हारा? V3 करने से
टॉर्क इंक्रीज
हो
हो
रहा
रहा है एंड फ्लक्स भी इंक्रीज हो रहा है सर सर इट कम्स
लेफ्ट साइड में फिगर है, कैसे हो रहा है बताओ?
सर हम जो
ऑब्वियसली को पता
स्टेटर
नहीं, तुम बहुत बोल रहे हो, तुमको बहुत पता है, मुझे पता है।
हाँ सर मतलब जब हम लोग मतलब टॉर्क इंक्रीज करेंगे मतलब रेफरेंस टॉर्क है सब जब हम लोग उसको कंपेयर करेंगे तब एक टॉर्क स्टेटस होगा तो उसको देखते हुए मतलब 1 आएगा तो इंक्रीज होगा ऐसा।
नहीं, वो वन तो आएगा, वो तो ये इंक्रीज जब ये सिंबल आएगा इंक्रीज करने के लिए तब तो वो वन आएगा हिस्टेरिसिस। लेकिन यहाँ कैसे पता चलेगा इंक्रीज होगा कि कैसे पता चलेगा? ये फिगर है ना, एक फिगर रखे हो ना, फिगर 10 में
हाँ सर।
एक लियो ना, स्टेटर फ्लक्स लियो ना 5s।
हाँ सर।
उसके एंड में जो तुमने एक बनाया V1 V2 V3 V4 जो V6, मैं सपोज V3 सिलेक्ट कर लिया,
हाँ
ठीक है?
सर।
तो फ्लक्स कैसे इंक्रीज होगा, टॉर्क कैसे इंक्रीज होगा बताओ?
सर फ्लक्स मतलब फ्लक्स तो एक्स एक्सिस में है तो हम जब V3 लेंगे तो फ्लक्स इंक्रीज होगा और टॉर्क
कैसे
वाई एक्सिस में है।
कैसे
पर
कैसे इंक्रीज होगा पता है कि नहीं? इलियास पता है?
सर एक्चुअली फ्लक्स लिंकेज को हम दो कंपोनेंट में डिवाइड करते हैं वन इज horizontal component which is psi alpha and another is vertical component psi beta
वो अलग है, वो अल्फा बीटा तो वो अलग है, वो तो तुमने 3 फेज 4 फेज करने के। यहाँ सिंपल बताओ फ्लक्स कैसे इंक्रीज हो रहा है, टॉर्क कैसे इंक्रीज हो रहा है, पता है?
actually sir psi alpha is responsible for flux and psi beta is responsible for torque. So when we will select B3, that means flux psi alpha and psi beta, that means it will be in like first quadrant, that means flux and torque both are in positive direction.
नो सिंपली तुम लोग ने एक दो इक्वेशन लिखा नहीं, लिखना चाहिए। जो स्टेटर फ्लक्स इंक्रीज होता है, जैसे V3 को सिलेक्ट किया ना,
Yes sir.
तो V3 जो है तुम्हारा वोल्टेज है, तुमने ले रहा है ना इधर से, जो हीटिंग देगा तो यही वोल्टेज तुम्हारा V3। जो जितना V3 होगा उसी हिसाब से फ्लक्स आएगा स्टेटर में, ठीक है? जो V3 की जितना आरो है हाईएस्ट है, ये सर
Yes
नो
sir. Yes sir.
V3 अगर सिलेक्ट किया तो उतना फ्लक्स आएगा, ठीक है? तो उनका रिजल्टेंट फ्लक्स कितना होगा देखो, इंक्रीज होगा कि नहीं हाईएस्ट से?
हाँ सर इंक्रीज होगा।
Yes
हाँ,
sir.
V3 बढ़ाया मतलब कि there should be some change in L highest, okay? The resultant flux will be increased and अगर तुम्हारा हाईएस्ट जहाँ है, रोटर फ्लक्स कहाँ होगा बोलो? हाईएस्ट स्टेटर फ्लक्स, रोटर फ्लक्स कहाँ होगा? लैग करेगा या लीड करेगा? दिस इज ए फेजर डायग्राम, यस और नो?
Yes sir.
हाईएस्ट तो स्टेटर फ्लक्स है, रोटर फ्लक्स कहाँ होगा? लैग करेगा या लीड करेगा उससे? अरे स्टेटर में पहले फ्लक्स आता है या रोटर में आता है?
तो स्टेटर में आता है पहले, तो वो लेग करेगा सर
रोटर फ्लक्स मतलब लैग करेगा, मतलब नीचे रहेगा कहीं, टोटल
हाँ
फ्लक्स
सर ले करेगा। यस सर।
जब फाई एस था, ठीक है, और फाई आर उसके नीचे रहेगा, दोनों में एंगल जितना होगा, फॉर एग्जांपल एंगल होगा, ठीक है।
यस सर।
अगर V3 चूज किया तो रिजल्टेंट जो होगा न्यू फाई एस, जो न्यू होगा, फाई एस न्यू और फाई आर के बीच में एंगल बढ़ेगा या कमेगा?
सर वो एंगल बढ़ेगा सर, B3
बढ़ेगा
स्विच
बढ़ेगा
करने
सर।
से।
समझ में आ रहा है ना मैं जो बोल रहा
हाँ
हूँ?
सर।
यस
हाँ
सर।
फाई एस प्लस V3, तो एंगल बढ़ने से टॉर्क बढ़ता है। ये जो एक्सप्रेशन दो तुमने लिखना भूल गया।
हाँ
वोल्टेज के
हाँ
लिए वोल्टेज इज रिलेटेड टू फ्लक्स, स्टेटर फ्लक्स, and the angle between stator flux and rotor flux is total depends upon the torque. Okay, अब
यस सर।
देखो V1 देखो, V3 देखो, V0 देखो, सारा में देखो वो तुम्हारा टेबल के हिसाब से मैच करेगा। Okay. और भाग्यश्री बताओ, VSI और CSI, एक VSI यूज किए हो ना, VSI और CSI इन्वर्टर में क्या बेसिक डिफरेंस है?
सर VSI और
CSI
सर VSI एंड CSI एक वोल्टेज सोर्स इन्वर्टर एंड ए करंट सोर्स इन्वर्टर है। तो
बताओ।
सर CSI मतलब CSI ड्राइव सर इंडक्टिव एनर्जी स्टोर करता है और VSI कैपेसिटिव।
अच्छा वो तो करता है, हाँ, ठीक है। वो डिफरेंस क्या है दोनों में इन टर्म्स ऑफ इनपुट वोल्टेज, इनपुट करंट? बोलो बोलो तो। सीएसआई में इनपुट वोल्टेज क्या रहता है, वेरिएबल या
सर
कांस्टेंट?
DC वोल्टेज, हाँ
कांस्टेंट या वेरिएबल रहता है
सर कांस्टेंट DC वोल्टेज है।
सीएसआई में?
CSI में
तो अब ये छोड़ो,
सर
बताओ दोनों में व्हिच वन इज
सर
बेटर?
इनपुट सर CSI इनपुट इज कांस्टेंट करंट सर इन
ओके,
CSI।
दोनों में कौन सा अच्छा है, व्हिच वन इज गुड, व्हिच वन इज मोर फिजिबल टू यूज?
सर VSI।
व्हाई? कैन यू चेंज a VSI to CSI?
सर एक्चुअली इन CSI जब सर VSI में जब शॉर्ट सर्किट होगा ना तब सर्किट को डैमेज कर सकता है, लेकिन CSI में ऐसा नहीं होगा, नहीं होता है मतलब।
सिंपली तूने बोला ना
आप जो
इनपुट करंट
समझते हैं।
कांस्टेंट रहेगा, तो इनपुट करंट, एक
हाँ
करंट कांस्टेंट सोर्स के लिए जनरेट करना इट्स वेरी मच डिफिकल्ट, इट इज कॉस्टलियर। ओके,
हाँ सर।
यस सर।
VSI क्लियर होता है। ओके, यू हैव डन ए गुड जॉब।